Hi, I am Jabas Daniel Guillermo, and today I will be discussing about thermoelectric generators and coolers. In this video, I will be giving a brief history and background about the thermoelectricity and the two devices associated with it, which is the thermoelectric generators and thermoelectric coolers. In each device, I will discuss about their operations, the theory behind that operation, and some of their applications. So let us get started. So already in 1794, Italian physicist Alessandro Volta observed that a metal rod which ends were at different temperatures caused a spasm in frog muscles. In other words, the temperature difference in the metal caused an electric current that excited the muscle. But because the concept of electricity was not clear back then, it was not until 1822 that Thomas Johann Seebeck rediscovered the same effect when he discovered the deflection of a compass needle close to two metal junctions that were kept at different temperatures. Together with the Peltier effect discovered in 1834 and the Thomson effect discovered in 1851, the Seebeck effect describes the sum of physical processes we know as thermoelectricity today. In 1948, the first commercial thermoelectric generator was developed in the USSR. It was mounted on top of an oil-burning lamp and was able to power a connected radio. Progress in processing semiconductor materials soon led to TEGs and cooling modules with higher efficiency and, as a result, to more commercial exploration. However, the success of thermoelectric devices was soon overshadowed by the massive progress and success in the battery sector. The thermoelectrics were pushed to niche markets such as power generation in space or Peltier cooling in optoelectronics and small refrigerators. But this was not the end of thermoelectrics. Today, TGs can be just a couple of millimeters small, less than a millimeter thick, and yet contain hundreds of thermocouples. As a result, significant amounts of electricity can be generated from temperature differences of only a few degrees. So let us proceed with thermoelectric generators or TEGs. Thermoelectric generators are solid-state semiconductor devices that convert a temperature difference and heat flow into a useful DC power source. Thermoelectric generator semiconductor devices utilize the Seebeck effect to generate voltage. This generated voltage drives the electrical current and produces useful power to a load. The Seebeck effect is a phenomenon in which a temperature difference between two dissimilar electrical conductors or semiconductors produces a voltage difference between the two substances. When heat is applied to one of the two conductors or semiconductors, heated electrons flow toward the cooler one. If the pair is connected through an electrical current, direct current or DC flows through that circuit. Here we will demonstrate the Seebeck effect by using a thermoelectric effect demonstrator and two cups. As you can see, one is labeled cold and the other is hot. The cold cup already has water inside. After we place the demonstrator inside the cups, we will pour in the hot water. Now both legs are immersed. One leg is immersed in the cold water and the other leg is immersed in the hot water. As the heat flows through it, it will create a current that will produce electricity. And what makes this possible is the Peltier module that's between the two metal legs. After a short while, we will notice the propeller will start spinning. Generally, you can generate electricity from every available temperature differential, but with a small differential, the generator power will also be small. So if you were to put cold water with ice on one side and boiling water on the other, it will result in more power being generated. Now let's remove the legs from the liquid and place it on the table. As you can see, it is still spinning. Now, the Seebeck effect is the production of an electromotive force and consequently an electric current in a loop of material consisting of at least two dissimilar conductors when two junctions are maintained in different temperatures. The conductors are commonly metals, though they may not be even solids. Now, the propeller will spin for a little short while until thermal equilibrium is attained between the two dissimilar conductors, and it will stop completely. Thermoelectric generators are solid-state devices. Having no moving parts to break or wear out makes them very reliable. Thermoelectric generators can last a very long time. As such, they are often used in applications where power is needed in an extreme environment. Some of these types of applications include spacecraft, Mars rovers, lunar power stations, power generation in Antarctica, flashing light buoys, lighthouses, and nuclear pacemakers. Thermoelectric generators have been used to recover and utilize waste heat from automotive exhaust, steel foundries, wood stoves, glass flares, candles, hot water pipes, solar photovoltaic cells, and electronics. Thermoelectric generators can be used to produce microwatt or milliwatt output levels, which is applied in wireless sensor networks for environmental monitoring, low power Internet of Things applications, body heat powered wristwatches, body heat powered flashlights, and body heat powered medical sensors. So let us now proceed to thermoelectric coolers or TECs. A thermoelectric generator is not the same as a thermoelectric cooler, which is also known as a TEC, Peltier module, cooling chip, or solid-state cooling. A thermoelectric cooler works in reverse of a thermoelectric generator. While thermoelectric generators are used to produce power, thermoelectric coolers or Peltier coolers are used for removing or adding heat. When a voltage is applied to thermoelectric cooler, an electrical current is produced. This current induces the Peltier effect. When the current flows through the junctions of two conductors, heat is removed from one junction and cooling occurs. Heat is deposited at the other junction. Cooling occurs when a current passes through one or more pairs of elements from N to P type. There is a decrease in temperature at the junction or the cold side, resulting in the absorption of heat from the environment. The heat is carried along the elements by electron transport and released on the opposite or hot side as the electrons move from high to low energy state. The small white plate here is the top of a thermoelectric device. We are going to demonstrate the Peltier effect using a droplet of water. This is also known as thermoelectric cooling or heating. The Peltier effect occurs when an electrical current is applied to a thermoelectric device. This causes one side of the device to heat up while the other side of the device cools down. This creates a temperature gradient on the device that is dependent on the direction of the electrical current. We will now apply a current to the device. As you can see, the temperature shown in degrees Celsius is decreasing. And as you can see, the water droplet has frozen. If the direction of the electrical current is reversed, the side that was cooling begins to heat and the side that was heating starts to cool. We will now reverse the direction of the electrical currents and heat the frozen droplet. As you can see, the temperature is increasing and the droplet begins to boil. Thermoelectric coolers offer a myriad of benefits when traditional cooling methods are unsuited, and they are therefore used in many applications, one of which are thermocyclers. Thermocyclers also are commonly used in biomedical settings to amplify DNA and RNA samples by polymerase chain reaction or PCR. Thermocyclers amplify segments of DNA by systematically raising and lowering the temperature of a block that holds the PCR reaction mixture. Another application is that of single-stage thermoelectric coolers, which are designed for medium to low heat pumping capacity requirements. Thermoelectric cooling has many applications in cooling, heating, refrigeration, temperature control, and thermal management. Typical applications include laser diode arrays in fiber optic systems and maintaining constant viscosity in inkjet printers. Thank you for watching.